So so let's get going. So I'm Sauravi. I am a PMRS fellow here at IISc, and this is a TA course that we're trying to do as a part of my TA requirements. So we were discussing about ensembles, starting with microcanonical ensemble in the last class, and today we will take it forward and we'll talk about canonical ensemble. Okay. So to just recap what we have been discussing, we started with the very idea of thermodynamics, which is a phenomenological description, and it's a macroscopic one. And then we saw that there's this statistical mechanics, which is a probabilistic description, and that can actually bridge or connect the microscopic description involving, microstates, which talk about position and momentum of individual particles or constituents, and then relate it to macroscopic quantities, which are typically defined in thermodynamics. Okay, so this link between the microscopic and the macroscopic description can be done by probabilistic description, and that's where the statistical mechanics comes in. And we saw that because there can be several microstates corresponding to a single macrostate, that means now using our well-known idea of probability, you can define a, a probability density, saying what is the probability that your probability, which is basically what are the number of microstates associated with a single one second. So we are just getting started, and this is in continuation with what we have been discussing in the last class as well. And in the last class, we spoke about microcanonical ensemble, where the idea was that it's an isolated system where there is no energy, the energy remains constant. So there is no transfer of energy with the surrounding. It's isolated. And so now keeping the energy constant, we wanted to see what is the number of microstates corresponding to a particular energy state, right? And from there, we could see that we can define, uh, you know, uh, a probability density. And considering that all the microstates are equally probable, we saw that it's a fixed quantity, which is given as 1 by omega, right? Second. Okay. Now what we'll be talking about is a canonical ensemble, and this is slightly different from what we have been discussing previously regarding the fact that now here energy can be interchanged. So you can have a system which can exchange energy with the surrounding reservoir, okay? And what remains constant is the temperature, not the energy, okay? So that's the difference from the last ensemble that we were talking about. Okay, so let's get going. We'll talk about some basic concepts. We'll talk about some well-known problems, and then we'll solve certain questions. And if there are any doubts, you can feel free to ask me, okay? So canonical ensemble, it generally, like you can define it as something like this, where you have a system with some energy Es, okay? And then there's a, so you can define a system with an energy Es at some temperature T, and then it can exchange energy with a heat bath surrounding it. Okay, so you call it as the reservoir with certain energy Er, and it's also at the same temperature T. Okay, now the heat bath along with the system, like these two together, makes up an energy E, and This together forms again a microcanonical ensemble. Why? Because the total energy, including the system and the reservoir, is still conserved. Okay. But individually, the system can now exchange energy with the heat bath. Okay. So you can write the total energy E as ER plus ES. Okay. And we would like to say or like to find out what is the probability Pi of finding the state system S in a certain microstate I with energy EI. That's what we want to find. Okay. So what you can consider is you can consider that, for a typical system, if you say that S has some energy, EI, then it's proportional to the probability is proportional to the number of microstates omega S EI. Okay. That is the number of microstates possible so that the system remains in energy EI. Okay. Now, because you can exchange energy between the system and the heat bath, you can also rewrite it as the number of microstates for which the reservoir is in energy E minus EI. Okay. So omega S EI is similar or is proportional to omega R E minus EI because the total energy is E and that is conserved. Okay. So now Pi is proportional to omega R ER and ER is nothing but E minus EI. Now, if you consider that the energy of your system is much, much smaller than the overall energy, the total energy E, then you can expand this term, in this way. Okay. And then what you get basically del E of K ln omega. Okay. That is nothing but we already know K ln omega is the entropy, right? So you can write it as del S del E. Okay. And that's can be equated to 1 by T. So what do you get? You get that this probability of your system being in a certain energy state EI is proportional to this factor. So you have this factor coming up now, which is e to the power minus EI by KT. So in the microcanonical case, this was a constant value. Okay, but now it has a energy dependence. Okay, so it's a weight factor that now has been added. So now Pi is proportional to e to the power minus EI by KT. Okay. Now, using the idea that, the total probability considering all the states should be normalized to 1, it should sum up to unity, you can actually find the, normalized probability density, and it would be given as e to the power minus EI by KT by summation over I e to the power minus EI by KT. So this takes into account all the possible states that are there. So this value here is basically summation over Pi, right? So now, if you have a continuous system where your variables are having a continuous distribution, then you have to replace this summation by an integration. Okay, and you can write it as something like e to the power minus beta, where beta is nothing but 1 by KT, and you replace E by the Hamiltonian, right? Because energy, like a Hamiltonian operator, is associated with the energy. So you can always write it as e to the power minus beta h. And then the summation here becomes integration. And the summation here becomes integration. And then you can write it as, so what are you doing? You are doing integral over the phase space volume. Okay, D3 P, D3 Q. This is your phase space volume. And then you have e to the power minus beta h. Why are you dividing by 1 by h to the power 3n? So if you remember what we had discussed in the last class, this comes from the uncertainty principle. So h to the power 3n, if you're considering a space in 3 dimension for n particles, h to the power 3n is the smallest volume in the phase space that one microstate can occupy. Okay, so that's why you are dividing it by h to the power 3n. So it comes from the uncertainty relation. Okay. So now once you have this description, this gives you the probability density for a canonical ensemble, which is written as rho C. Okay. Now the denominator here is very important. Okay. This term here that you have in the denominator is referred to as Z, and that's the canonical function. That's the partition function. Okay. So now this partition function, as we will proceed, we'll see that the partition function has the information about the different thermodynamic potentials, or all the observables that are there. Typically we can derive all those information from this partition function. Okay, so this is a very useful, important measure, right? So typically you would write the canonical uh, density, probability density, as e to the power minus beta h by z, where z is your partition function. So this is your canonical partition function. Now we already know the definition of how we have defined entropy in terms of the probability density, right, in the last class. So we can use the same definition here, but now the probability density expression has changed because of the canonical description. So this would be written as, basically you are finding the expectation value of minus k ln rho, right? So if you explicitly write it, this is how it would look like. You're doing an integration over the phase space volume. So what you can do is, basically now you can rewrite, explicitly rewrite this term, k ln omega c. So you can write it as k beta h plus k ln z, right? So what this gives you is, this gives you the relation between entropy with the expectation value of Hamiltonian, which is nothing but the energy is associated with the internal energy of your system. And then you have k ln z, where z is your partition function. So this relation is very important, right? So now what you can do is, you can rewrite it in terms of the internal energy and rearrange the terms. Okay, so you can write beta as 1 by kt. And what will you get? You see that u minus ts will be given as minus kt ln z. And from thermodynamics, we know that U minus Ts is nothing but the free energy. So this now relates another thermodynamic potential called the free energy, Helmholtz free energy, with with the partition function. So if you know Z, okay, you can just find this value to actually find the free energy. Now, once you know the free energy, okay, this is a very useful relation. So once you know the free energy F, you can use different relations to find the different thermodynamic potentials. Also, what you can look at is, basically you starting from this relation that del S del U is equal to 1 by T, okay? So you can explicitly write S as a, considering that your canonical partition function is only a function of u via beta, which is 1 by kt. Okay, so if you consider that, you can rewrite it in terms of the partial derivatives. And interestingly, you get this relation. So this relation by itself is very important. What are you saying? You are saying that if you get z, which is your canonical partition function, you can do a derivative of del del beta k ln z, and that will directly give you the internal energy. U is your internal energy, right? So once you know Z, you can directly do this, find the expression value for this expression to find the internal energy. Otherwise, what you can do is, you can try to find the free energy, and then from there, try to define an equation of state and try to find the internal energy from there. You would get the same result, but this is something which directly relates the partition function with the internal energy. Okay, so this is the relation. It's a very important relation to remember. Okay. So now let us look at some of the examples which would actually give us an idea about how to, make use of the relations that we were discussing so far. So this is for a system of n ideal gas molecules in 3 dimensions. So in 3 dimensions, we know that it's a ideal gas molecule. So it will have a Hamiltonian given as p square by 2m. And there are n such molecules in 3 dimensions. So your number of coordinates run from 1 to 3n. Okay, so this is your expression of your Hamiltonian. Now here, again, you have to remember that for these questions, you have to be careful about whether the molecules or the constituents are distinguishable or not, right? So for this case, we know that there are n molecules in a volume. So you can consider that these molecules are all identical and they are indistinguishable, right? So for that case, you have to include the Gibbs factor, which brings in this 1 by n factorial term. If the molecules are distinguishable, in that case, you won't have this 1 by n factorial coming in, right? Now, once you know the Hamiltonian, we know the expression for the partition function, right? It's nothing but this integral over the phase space volume, right? E to the power minus beta h over the entire phase space volume, and then you normalize it by h to the power 3n, which is coming from the uncertainty relation. This is the smallest volume for one microstate, and then you divide by n factorial because these are indistinguishable particles, right? Now, for this question, when you put in the value of the Hamiltonian, what do you get? So here you have to see that the Hamiltonian is only a function of the momentum, right? So that means you can take this term d3nq out of the integral, right? So what will this d3nq be if you take it out of the integral? So you can understand that for one particle, okay, d3q is nothing but the volume, right? And now you have n such particles in that volume. So basically d3nq will be nothing but v to the power n, okay? So the integral now, what remains is this, okay? So you have 3n such integrals, while each of the integrals are independent of each other. So basically, you can write it as a product of multiple integrals, while where each integral takes up this form. D rho dp is some like dp nu is one momentum coordinate, and you write it as e to the power minus beta p square by 2m, which comes from here, right? So you have 3n such integrals, product of 3n such integrals, right? So here at this point, we will use a very well-known, standard result of Gaussian integrals, which tells us that minus infinity to infinity dx e to the power minus x squared is nothing but root over pi, okay? And with a substitution given by this relation, you can actually evaluate this integral, okay? And what you get is something like this. So this is your expression of canonical partition function for n ideal gas molecules in 3 dimension, okay? So this term here, you can, simplify it by considering, writing, taking up this term as lambda, and this is how it would look like. Okay, so you can understand that this is quite a simplified expression now. And once you have Z, now what you can do is you can try to find F, and you can try to find all the other different thermodynamic variables. Okay, so what you can do is you can write F, which is nothing but minus KT ln Z. Okay, and this is how it would look like. Here, once you know F, you can try to find the pressure, which comes as minus del F del V at constant temperature and number of particles. Or you can, now once you get this expression, you can get a equation of state from there. Okay, so PV equal to NKT, which is again the ideal gas equation. So you are getting back the same expressions that we had initially seen in thermodynamics. Okay, again you can find the expression for entropy. Okay, so this is how it would look like, or the chemical potential. So all these different values you can try to find out. You can also find the internal energy, okay, and that is given as 3 by 2 NKT. So, and that also matches with our classical description, results, right? If you have n ideal gas molecules in 3D, we know that the internal energy is given as 3 by 2 NKT. So basically, you're getting back the same results of what you had seen initially in thermodynamics, but now you have started from the Hamiltonian, which takes into account the microscopic, description of the molecules in the system. Okay, and all of this comes from the canonical partition function. So the first step in this kind of questions is always to find the partition function. Okay. Now, there can also be questions where you're talking about ultra-relativistic gas. This is one such example where now you have to calculate thermodynamic properties of P, where this is the modulus of the momentum into C. Okay, so this is an expression of the Hamiltonian for ultra-relativistic gas. Okay. So for this case, again, what you have to do is you have to first, you want to find the thermodynamic properties. So for that, you have to first find the canonical partition function. Okay. So what do? You basically try to find this integration, right? So here again, your Hamiltonian is only a function of the momentum. So you can take the d3 and q out of the integral. You get v to the power n. And this is your expression. This is the integral. Now what you have to find. Okay. So at this step, there is a change of coordinates that we'll be doing. Now, why so? First is you have to look at the fact that in the Hamiltonian, you have the modulus of the momentum. Okay. So what does this mean? You basically have, so if you look at three-dimensional, like if you look at x, y, z coordinates, it's nothing but square root of px square plus py square plus pz square, right? So this term tells you that it's a function of, so if you consider a sphere in the momentum space, this tells you that the radius of that sphere is given as p nu, right? So basically what you can then therefore do is when you are writing this integral, okay, what is d3 p nu? This is nothing but, so if you want to write it in x, y, z coordinate, it is nothing but dpx, dpy, dpz, right? So ideally what you have is here dpx, dpy, dpz, and then you have e to the power minus beta into square root of px square plus py square plus pz square into c, right? So what you can do is now you can try to decouple the individual px, py, pz terms and do an integration. That's possible. You can do that. But what's way simpler is that if you now go from the, Cartesian coordinates to the spherical polar coordinate, where you consider that now you consider a sphere of a radius p, okay, which is given as the modulus of your momentum, okay. So then the volume element here goes as 4 pi p squared dp, and you have e to the power minus beta cp, where p runs from 0 to infinity, okay. So that's how you're going from a Cartesian coordinate system to now a spherical polar coordinate system, okay. And you have n such integrals, so therefore to the power n. Now, this is again a standard integral. So what you can do is you can replace beta Cp as x, okay, and rewrite it. And this is the standard expression for a gamma function, okay. So that means now you can replace and evaluate this integral, and this is the form that you get. Okay, so this is your partition function for a ultra relativistic gas. So these are very standard problems which typically come up in different questions, and it's a good practice to actually solve it by hand. Okay, so while I'm discussing, you can also try to solve it by yourself so that you get an idea about how to do the substitutions and where to use what kind of relations. Now, once you have the partition function, the rest is same step. Okay, so you can use the expression of minus kT ln z to find the free energy. Here, if you want to simplify, you can use the Stirling's formula for ln n factorial. Okay, and then you can, from the expression of F, you can find the pressure, you can find entropy, chemical potential, energy, all of it. Okay, so again, here you get it as 3 kT, right? So till now, is there any confusion that you have? If there's any confusion, please feel free to ask. Okay, is it clear till here? Also, you can write it in the chat box in case if you have any doubt or anything. Okay. Okay. So I'll consider it's clear. In case there is any doubt, you can stop me and ask a question. Ask the question. Okay. Okay. So now these are all very standard problems. Okay. So and please practice them and like you at least try to solve it once. Now here it says that you have harmonic oscillators in a canonical ensemble. Okay. So you have n distinguishable harmonic oscillators of frequency omega. Important point to note is distinguishable, right? So because it's distinguishable, now you will not have the Gibbs factor, right? And I hope it's clear why we have the n factorial when it's indistinguishable and we do not have it when it's distinguishable. If there's any doubt, you can ask, okay? So now we know the typical expression of Hamiltonian for a harmonic oscillator, right, of frequency omega, and it's given as p square by 2m plus half m omega square q square. And you have n such oscillators, so your nu goes from 1 to n, right? So again, you have to find the partition function. So here you do not have the n factorial because it's a distinguishable system of particles. So what for this case, now your Hamiltonian depends on both momentum and position. Okay. So that means you cannot take d and q out of the integral anymore. Okay. You have to do an integration over q and p both. So what you can now do is you can explicitly, write group the terms which involves q and the terms that involve p. Okay. And this is how it would look like. And there again, you have to do the substitution accordingly so that, you can use the standard Gaussian integrals. Okay. It's the same integral that we have used previously. And if you use that integral, you would get an expression for the partition function, which is very simple, right? You see, you get it as kt by h cut omega to the power n. And again, you're getting this ratio where you talk about, thermal energy to this h cut omega, which is associated with the energy states if you talk about harmonic oscillators, right? So this is an important, interesting point to know. And now once you have the, expression for the partition function, you can try to find the free energy, which is minus kT ln z. So this is how it looks like. And from here, you can find all the other terms. Okay. Now, interesting to note is that the pressure goes to zero here. Why is it so, right? So you have some harmonic oscillators, they are oscillating about their mean position. And why does the pressure turn out to be zero in this case? So if you always, when you get this results, try to, also understand what it means physically. So this is happening because you have this harmonic oscillators localized in the volume, right? They are not free to move anywhere. They're moving only about their mean position. So that's why the the pressure is nothing but, the momentum transfer that happens when these molecules go and hit the surface or the boundary. So that is not happening here. So that's why the pressure is zero. Okay. And you have entropy, you have chemical energy, and you can also find the internal energy of the system. So all this can be derived directly once you have the expression for the partition function, right? Okay. Now, initially what we discussed in the last question was for a classical harmonic oscillator where the Hamiltonian was written as sum of kinetic energy and potential energy. So P square by 2m plus half a omega square Q square. Now the question says that you again have n, harmonic oscillators, but these are quantum mechanical harmonic oscillators. Okay. So here, what do you think should be the change, right? How should my expressions change? Is there any idea, anything that you want to add to it? Like what comes to your mind? So now you have n quantum mechanical harmonic oscillator. Initially, we spoke about classical oscillators. So how will the Hamiltonian say, like how will the Hamiltonian change? The idea? I hope you're understanding, like, or like n quantum mechanical harmonic oscillator. So what is expected to change when you go from the classical description of a harmonic oscillator to a quantum description, right? Quantum mechanical harmonic oscillator. What is the first thing that will change? Any idea, guys? Hello? The first idea that should come to your mind is like when you're talking about quantum mechanical systems, so now the energies will be quantized, right? So initially, when you wrote energy like Hamiltonian as this, it's a continuous function, but now you will have quantized energy states, right? So from our basic idea of quantum mechanics, what is the expression of the energy states for, some harmonic oscillator? How are the energy states defined, right? That will tell us how the partition function would be, right? Because that's how you find the partition function, right? You need the Hamiltonian in order to define the partition function. So basically what I mean is that now if you just take one harmonic oscillator, we know that the energy states are given as n plus half h cut omega, right? So now your partition function becomes a summation. So it's a discrete system now, and it has a summation over n, where n goes from 0 to infinity, and you have e to the power minus beta h cut omega n plus half. So this is your energy states for the harmonic oscillator. You're first finding it for one particle, okay? And then you can, take this e to the power minus beta h cut omega by 2 outside the summation and consider all the n terms with the n here. So to the power n it will be, and then this is how you can write it. So this is just rewriting the term. That's the expression for your partition function for one harmonic oscillator, right? So what you can now do is basically you can try to, you know, use the identity for the geometrical series and rewrite it explicitly, and it would take up a form like this. Now you have to find the partition function for n quantum mechanical oscillation, right? So what you do, you say that the n particle partition function is given as, so if you know the partition function for one particle, then for n particles is nothing but to the power n, okay? So here it's important to point out what is the condition that is required so that we can use this relation, right? So if you know the partition function for one particle, and now you're writing the partition function for n particles as to the power n, okay? So when will this hold? What is the condition? What is the assumption behind writing this? Okay, that's important to know. Can you always write this term? So if you know the partition function for one particle, can you always write the partition function for n particles using this relation? Or is there some underlying assumption that we are considering while we write this? Okay, that is very important to know. Okay, any idea why is this, why are we able to write it like this? Because see, this is how basically now you have -1 here, it becomes minus n, so that's your net partition function, right? But is it always true that we can write it this way, or under what conditions can we write it? That's something that one has to know. So you have to remember that if you know the very idea of, even like typically when you talk about probability as well, when there are independent events, okay, so we write the net probability as a product of those independent events, right? So here, when we are trying to find the, partition function for n particles, if you consider that the particles are non-interacting, okay, so the particles are non-interacting with each other, then the individual partition functions for all the particles are independent of each other. So then you can use this relation. If they're interacting, then this is not true. Okay. So whenever you are writing, you're trying to find for one particle and then you're writing for n particles as to the power n, you are assuming that the particles are not interacting with each other. So now this is your expression of your partition function. Now, once you know the partition function, okay, here again, there is no Gibbs factor. Why? Because you're talking about distinguishable system. So 1 by n factorial is not there. So now once you have the expression for your partition function, you can try to find the free energy. So this is how the free energy term will look like. From here, you can again find the chemical potential or the pressure or the internal energy as well, right? And again, here you can see you have this. So the 0 point energy does come up, okay? N by 2 h cut omega. This term comes up here, which was not there in the like in the classical case, right? Okay. Now, N quantum mechanical harmonic oscillators, right? So whatever expression you have found for the free energy, you can right now try to find the expression for entropy. And this is how the expression for entropy will look like. So while I'm discussing and directly showing you this, this expressions, I would always ask you to, at least try to solve it once, okay? So that you know how we are getting to this points. Like try to solve it by hand. So now once you have the entropy, okay, this is your expression for entropy. You can write the internal energy as something like this. So again, this half n h cut omega, which is your 0 point energy, and then you have this term here. Now this term can be, written as a mean quantum number. Okay. So in a way, this has the information about how the particles are distributed in the different states, different available states. Okay. So later we'll see that based on what is the distribution of the particles in the different states, this expression would change. So this has the information about the distribution, and this is called the mean quantum number. So now what you can do is you can write an expression for the average, energy for the nth state, which will be given as half h cut omega plus this mean quantum number, mean occupation number n into h cut omega. Okay, and once we go ahead with the course, you see that this would have a lot of physical significance as well when we talk about particles having different kinds of distributions in the different available energy states. Okay, so that's how we can from a very general point of view, starting from the Hamiltonian, we can actually find the expressions which do hold true when we talk about thermodynamics or when we talk about quantum statistics. Okay. So now, based on what we have discussed so far, we'll try to solve some questions. Okay. It says that you have a system of n non-interacting classical particles, each of mass m, in a two-dimensional harmonic potential of the form given as alpha into x square plus y square. Okay. So now the canonical partition function of the system is given as how much? Okay. So I would give you a couple of minutes. Please try to solve it based on what we have discussed so far. So we have already solved questions similar to these where we have discussed about, harmonic oscillators. But now based on the question, the exact form of the question, what you have to do is the potential, when you have non-interacting classical particles, okay, and because they would have some kinetic energy, some potential energy. So based on that, you can define the Hamiltonian. Once you define the Hamiltonian, you know how to find the partition function, right? You have to make use of the well-known, Gaussian integrals that we have discussed, and that will give you the answer. Just try to, at least work out the main steps so that, you get used to solving this kind of questions. If you are stuck somewhere, please let me know, okay? You have to use this Gaussian integral. You will do the substitutions accordingly, and then the integrals will have this form. You have, there can be a factor difference in the answer. I mean, some constant values can be slightly different, like the coefficients, but you'll see that one of the results will match the best with the available options. So basically, this is your expression of potential, right? So now if you want to find so you can make use of the fact these are non-interacting classical particles. So you can first find the partition function for one particle, and then for n particles, it will be nothing but that to the power n, right? So for one particle, how will it look like? So you have px squared by 2m, py squared by 2m, and then so in the Hamiltonian will look like px squared by 2m plus py squared by 2m plus alpha x squared plus alpha y squared, right? And now you have to do this integration over the phase space volume. So you can separate out the px, py, and x and y terms. Okay, each of them will be a Gaussian integral. Okay, and as you can see, you have 1 by h squared. Why? Because you're talking about a two-dimension. Okay, and you're talking about a single particle here. So that's why you have two pairs of p and q, right? So that means using the uncertainty principle, you know that the smallest volume in the phase space occupied by a single microstate is given as h square. Okay, if it was three-dimensional, it would have been h cube, right? So now this is your partition function for one particle. And then for n particles, it will be z1 to the power n, right? So you can try to explicitly solve this integral, and there you have to do the substitutions so that you can use this Gaussian integral identity. So I mean, this would look something like this. Okay, if you put in, do the substitutions and use this identity, this is how it would look like. For one particle, this is how it will be, and for n particles, we'll have to the power n. So here you can see this matches best with this term here. You have a h squared, which is not written here, but h square will be there. So that's a difference. But otherwise, this is the term that matches the best. So this is your option. Okay. I hope it's clear. Now you can also have questions like this, which are quite straightforward. Okay. And it directly comes from the idea of how microstates can be distributed, or particles can be distributed in the different energy states. So it says that you have n distinguishable particles, and they can be in two states, either 0 or epsilon. Okay. And it says that the total energy is N into epsilon, where N is some integer. So now you have to find the entropy of the system. Okay. So if you recall and remember the basic definition of how you define entropy for a system like this, you'd be you can tell the answer right away. Okay. So any idea what the answer should be? So use the fact that how do you define entropy? So you basically define entropy as, it's associated with the number of ways in which you can have number of possible microstates, right? So if you remember, entropy was given as something like KL and omega, where omega was your number of microstates. So now for this case, what is the number of microstates? How do you find that? That will give you the answer. It's quite straightforward. See, this things should be very clear because as we proceed with the courses, the things will gradually become more involved and there'll be many other concepts coming in. So these ideas should be clear, okay? Basically, number of ways in which you can choose smaller number of particles from a capital number of total particles is given as NCN, right? So that means your omega or W here, it gives you the number of ways in which you can have your microstress. So that is given as NCN. And this is how it looks like. So now entropy is proportional to omega or W for this case, right? So entropy is given as KLN omega. So the answer would be D. Okay. Very straightforward question. Okay. Let's move on. Now here it says that you have rotational energy levels of a molecule and they are given as EL, okay, where L can go from 0 to, all different numbers, integers. And now I naught is the moment of inertia, the contribution of rotational motion to the Helmholtz free energy per molecule at low temperatures in a dilute gas of these molecules is how much? So there are a few things. First is you know the energy levels, okay? And you're talking about rotational energy levels of a molecule. And then here you want to find the expression of free energy per molecule. And then go to the low temperature limit and see what is the contribution of this rotational motion to the Helmholtz free energy, right? So basically, you have to find an expression for F and then see how it looks like at low temperatures, right? Given the energy levels, EL as h cut square by 2 I naught L into L plus 1, okay? How do you think we should address the question? So first point is we have to find the partition function, right? For finding the partition function, what do you need? You need the energy levels which are already there. For this kind of question, there are certain things that one should remember. And any idea what that should be? So for this kind of question, there is this one thing that you should, use is that when you are defining energy states, they can also be degenerate. Okay, that means you can have you can put particles in that state in multiple ways. Like there can be multiple states with the same energy level. That's the degeneracy that can come up, right? So for rotational energy levels, you do have a 2L plus 1 degeneracy. Okay, so you need to be careful about that for this question. So what it means is now you know that the energy states are given as h per square by 2 I naught, L into N plus 1, where L goes as 0, 1, 2, dot, dot, dot. Now when you write the partition function, okay, now this is again a discrete system, okay, it's not, so we have to do summation. And how will the summation be defined? So basically you are doing a summation over e to the power minus beta h, and then you are multiplying each energy term, okay, with the associated degeneracy. For rotational energy levels, we know the degeneration is given as 2L plus 1. Okay. So this is how your partition function will look like. So now what you can do is you can do, okay, so this L, this should be 1. Okay. So you can put L equal to 0. So what you get is 1. And then the next term from L equal to 1 to infinity is given by this relation. So now you have Z in terms of, in a form given as 1 plus X kind of form, right? So you can consider this as X. So basically now you have Z is equal to 1 plus X kind of form, right? You have to find what? You have to find the free energy. So basically you know Z, you have to find free energy means you have to find L and Z, right? So for that you can use this identity. Ln 1 plus X is given by this expansion. So here, why are we using this is because we have to see what happens at low temperatures, right? And here in this exponential term here, you have kBt in the denominator. That means for low temperatures, higher temperature terms can be neglected, right? So because the temperature is low, that means the smaller this value, the bigger will be this entire value, and you have e to the power minus that term. So it will be gradually decreasing quite fast, right? Decaying, exponentially decaying. So that means you can only take the first term, and that should suffice, right? So that's what you can do. So when you find F, you have to find KT, L, and Z, right? And there you can use this expansion. Okay. So that means F will then be given as minus KBT. Ln 1 plus X is nothing but, so you can just take the first term, which is X. So this term, right? This should be from 1. Okay. L equal to 1 to infinity, 12 plus 1. This is how it looks like. Okay. So this is your expression for F. Now you can see this does not entirely match with the options that you have here, right? So you have to do for some more, simplifications or modifications to this form. What can be done, right? So what can you do here? You have to look at the effect at low temperature and in a dilute gas, like what's the situation, right? So if this is now your expression for F, what additional condition can you impose, right? That's the question. So basically, you can see that as your temperature, if it is a very small value, then this term will be quite large. So the decay will be quite fast. So you can just consider the first value of L, right? So you can write it as KBT into, do an expansion. And when you write only the first term would be effective, because as you go further, it would be again, decaying further. This will not be so significant. So that means at low temperature, this is how your expression should look like. Okay, so this is your answer, right? So for this kind of questions, you need to be careful about how are the energy states defined, okay, energy levels defined. And if there is any degeneracy in the energy state, you have to consider that while you calculate your partition function. Okay, be careful about that. Rest follows. Okay, based on whatever limit you have to use, low temperature, high temperature, you can use the expansions accordingly. But this is the fact that you do have to consider the degeneracy in the energy levels if there is any. That is an important point to remember for this kind of questions. Okay. Okay. Now question 4. It says that the vibrational motion of a diatomic molecule may be considered to be that of a simple harmonic oscillator with some angular frequency given as omega. Now, if a gas of this molecule is at temperature T, what is the probability that a randomly picked molecule will be found in its lowest vibrational state? So you need to find the probability of finding a particle at its lowest vibrational state. Okay. So it comes from the basic definition of how you define the probability density for canonical systems. When you know the Hamiltonian, okay, how do you define the probability density? That's where this the answer lies. Okay, I'll give you another couple of minutes. Please try to work it out. If you can define, okay, how do you define the probability? If you can, use that the basic definition, the answer will be quite trivial. It's quite simple, I guess. Like, I don't know, like if you are stuck, I'm not sure. But basically, you define the probability as e to the power minus ei by kt. We at the very start, we did see that for canonical ensemble, the probability for a particle to be in a particular energy state is given as is proportional to e to the power minus ei by kt. And then when you normalize it by the partition function. So pi is given as e to the power minus ei by kt by summation over I e to the power minus ei by kt. Right? So for this case, you have two energy states, or how many? No, you don't have two. You have, so this is a harmonic oscillator at angular frequency omega. So you can define the energy states as n plus half h cut omega, right? And you have to find what is the probability of being at the lowest state, right? So we know that the energy states are given as e to the e equal to n plus half h cut omega, where n goes from 0 to uh, you know all the integers. So that means you can write z as e to the power minus h cut by half h cut omega by kt plus e to the power minus 3 by 2 h cut omega by kt and so on, right? So here you can, use the geometric series identities and try to find z. Okay? And you have to find the probability of being in the ground state. Now, for the term corresponding to the ground state here is this. So that means in the numerator, you should have e to the power minus half h cut omega by kt. And then this is your z. Okay. Basically, you're just putting the values here. So now what you can do is you can take e to the power minus h cut omega by 2 kt common. So these two terms will get cancelled. So you have 1 plus this term here, where you can make use of the identity for the summation over geometric series. And this is the answer that you would get. Okay, so that means the answer would be A. Okay. Any question till here? I hope not. If there's any, please feel free to, stop me and ask, okay? Don't hesitate in case there's any doubt. Okay. Now here it says that you have energy levels. There are three energy levels. They're defined as 0, delta, and 2 delta. Okay. And a gas of these molecule is in thermal equilibrium at some temperature T. You have to find the specific heat at constant volume in the high temperature limit. High temperature means KBT much greater than delta. And there you have to find how the specific heat varies as a function of specific heat at constant volume. How does that vary as a function of temperature? That's the question. Okay. So how do you start here? So you know the energy levels. Okay. So that means you can find the partition function. And you can, from the partition function, you can also find the free energy, right? You have to find the specific heat at constant volume. So that means in a way you have to find the relation that relates free energy with specific heat. Okay, or how does specific heat vary as a function of temperature? So you need that expression so that you can look at the temperature dependence, right? How to proceed with that? Like, can you first just find an expression for the partition function? That's quite trivial, right? You have three energy states. You just have to find the partition function. These questions are quite, like, I mean, to some extent it's common. Some steps are common, but there are new nuances that come up, okay, at certain steps. So be careful to, notice them. So if you are trying to solve the question, I'll give you some time. Otherwise, we can also discuss the solution. Any idea anywhere you are stuck or anything, or are you trying? So see, here first part is very simple, right? So you have to find the partition function. You have three energy states, right? So basically you can write Z as e to the power 0 plus e to the power minus delta by kt plus e to the power minus 2 delta by kt. free states. So Z is nothing but summation over e to the power minus ei by kt. So this is how it looks like. Okay. So here, once you know the expression for Z, you can try to find the expression for the free energy. So here the free energy is written as A. Okay, so A is given as minus kBT ln Z. Okay. So what you can do here is you can, because you are in the limit where delta is by kBT is much, much less than 1, you can, use the expansion, use the series for this exponents and simplify the terms. Okay. So this is how your expression for A will look like. What you have to find is how does the specific heat vary as a function of temperature, right? So that means you need to find an expression for the specific heat. Okay. What you will have is a expression for the free energy. So you need to find a relation between the two. Okay. How to do that? So here, if you use, something which we just discussed at the very start of the class, that you can always write the average energy or the internal energy U as given as minus del beta of ln Z. Okay. So now what you can do is you can rewrite, ln Z as F by KT, minus F by KT, right? So what that gives you U as del beta of F by KT. Okay. And beta is nothing but 1 by KT. So that means now you can also write the same, like you can, change this partial derivative in terms of temperature. Okay. And that will be minus KT squared del T of F by KT. Okay. So if you explicitly write it, this is how it would look like. So this is your expression of U or the internal energy or like average energy in terms of the free energy and the derivative of free energy with respect to temperature, right? What you have to find? You have to find specific heat. That means you have to find del U del T, right? You know the expression of U. This is U. You want to find del U del T. So you have to do another differentiation, right? So that means this is del A del T, right? And you can find del square A del T square from here, correct? So if you simplify, this is how the form will look like. Now you, from here, you can see that if you want to find, this is your expression of U, right? And if you want to do du dt, which is Cv, you want to find Cv, right? So Cv is nothing but du dt. So what will you get? You will get a del f del t minus del f del t, and then you have another t minus t into del square f del t square, right? So then Cv becomes del square, just ignore those spikes. Anyway, they'll not write. I think the expression is written in the next. So basically, once you know this expression, from here you can do another derivative to find the Cv, right? So from here you can go to the expression of Cv by doing a derivative, del U del T. So what will you get? You get this expression. So Cv is given as minus T into del square A del T square. This A is nothing but F, okay? The free energy. So that means in the question, once you know A, you can find del A del T, you can find del square A del T square, then you can use this relation to see how it varies as a function of temperature. Okay. So for this case, the answer would be D. Okay. So this is how you can solve for this kind of questions. Yeah. I hope it's clear. Now here it says that a particle is confined in a region x greater than equal to 0 by a potential which increases linearly, given as u equal to u naught x. Okay, so it's a linearly increasing potential. You have to find the mean position of the particle at a certain temperature T. Okay. So how to do that? So what do you mean by mean position? Right? It's nothing but finding the expectation value of x, right? Your particle is it's an one-dimensional problem, and you have to find the mean position of the particle. That means nothing but you have to find the expectation value of x. Now, how if you go back to your basic definition in probability, how do you define expectation value? That's nothing but doing so finding the mean or the expectation value is nothing but doing an integration of that quantity multiplied by the probability density and doing an integration over the entire phase space volume. That's the basic definition, right? So now for this case, okay, so you know this is how the potential is, right? So can you define the expression for the probability density? Because once you have that, you can just multiply it with x and then do an integration to find the mean position, right? Can you try solving it? These are very straightforward questions. See, you have to find the partition function first. So partition function, how do you find it? So you have a particle, so it would have some kinetic energy given as p square by 2m, and it would have a potential energy which is given as mu naught x, right? So that means for one particle in one dimension, okay, so that's why you divide by h. This is how you find the partition function, right? Now, once you know the partition function, you can find an expression for Px. Px is nothing but the probability density, right? And then how do you define the mean position? It's nothing but the expectation value. So x into Px dx dpx. Basically, multiplying that quantity, whatever you want to find the mean of, you multiply that quantity with the probability density and do an integration over the phase space volume. That's the mean value, or that's the expectation, right? So that's what we have to find. So now once you have z, okay, what you can do? So here the expression of z comes in the denominator. What you have at the numerator is nothing but x into this term, right? So x into e to the power minus p square by 2m kbt dp into e to the power minus mu naught x by kbt dx, right? So now what you can do is you can see this, the terms involving the momentums are identical, so they can be cancelled. So you would have only the terms involving dx, okay? And then you can use, just explicitly, solve for this, and you would get, so 0 to infinity t to the power minus t dt, and here you only have 0 to infinity to minus t dt. So then you can explicitly, solve for this term, and that would give you an expression for, so then you have to also put in the values of the limits, and then what the solution turns out to be is t by mu naught. Okay, so that's how you can. So now if it was x square, then you would have to have a x. So you would have a t square term here. Basically, this would this. That was my point. So this would again be x square in that case, right? Now, if you have to find, the standard deviation or the variance, so accordingly you can try to solve for all those different terms. Okay, based on this kind of integrals. Now, here it says that you have a system of n non-interacting spin-half particles displaced in an external magnetic field H. The behavior of the entropy of the system as a function of energy is given as which of the following. So if you remember, similar things has been discussed in the last class as well. So if you remember, you can tell me what the answer is. Otherwise, what you can do is you can try to solve for this. How will you do it? So you have n non-interacting particles. These are spin-half particles placed in an external magnetic field. So now, because it's placed in an external magnetic field, you know the typical energy states that are possible. Okay, because they are non-interacting, you can start with one particle and then just have to the power n for n non-interacting particles, right? So for one spin-off particle placed in an external magnetic field H, you can use the idea that there'll be, energy levels dependent on this magnetic field H. And then based on the different energy levels, how will you find the partition function for one particle and then find for n particles? And once you have the partition function, you can find the the energy. From there, you can try to find the entropy. Or what you can do is you can look at in how many ways can you rearrange, directly look at try to count the number of microstates possible. So even from there, once you find omega, which is the number of microstates, you can do a k, l, and omega to find the entropy. Okay. So that's how you can find the expression for the entropy in terms of energy. Okay. What do you think the answer should be? So this is something which we have also discussed similar things in the last class. So from there, what do you think the answer should be like? Just try to consider the fact that you would have two energy states and then you have a spin half particle. You want to, you can have the particle in either of the states. And then accordingly, you can define what are the number of ways in which you can have that particle for a particular energy state. And then if you have n such particles, right? Basically find the number of microstates possible and then use the relation that is equal to KL and omega. So basically, this is how it would look like. So when you would actually, you can consider the energy states given as, plus minus mu h, right? And then from there, you can just define it as what are the possible ways in which it can be in one of the states, and then replace the, what do I say? Replace the value of n in terms of energy, because the number of occupancy and the energy they're all related, like linearly, proportionally related. So from there, you would get an expression for entropy, which would look like this. So what you can see here is that entropy is symmetrical about energy. So this fact by itself, okay, tells us that the answer should be A. Okay, it's symmetrical about energy. And another important thing is that when you have, this is also something we have discussed in the last class. So because when you're talking about systems with discrete energy levels where there is a discrete upper level of energy, then you can have this regions of, negative, where's my pointer? So you can have this regions of negative, temperatures. Okay, the negative slopes, which means negative temperature. That can come up when you have, uh, you know, uh, a limit to the maximum energy that your system can have. Okay. So here again, you have non-interacting particles, n non-interacting particles in thermal equilibrium. Each particle can be in any of the possible non-degenerate states, 0, 2 epsilon, 4 epsilon, the average energy per particle of the gas. So this is a very straightforward question. So here you have to remember in the last case when we talked about the mean position, okay, what did we do? We multiplied x with the probability of being at that position x and did an integration, right? So here it's a discrete, it's a problem with discrete energy levels. So the integration will not have integration, will have summations, right? But when we talk about average of a quantity or the expectation value of a quantity, what we basically mean is that quantity into the probability of being with that quantity, right? So energy would be like 0 into probability of being in the 0 state plus 2 epsilon into probability of being in 2 epsilon state plus 4 epsilon into probability of being in 4 epsilon state. So that would give you the average energy per particle, right? So now you have to find the expression for the probability of being in these different states, okay? And that is nothing but, it goes as e to the power minus ei by kt divided by the partition function. That is something we already know. So what you have to do, you have to first find the partition function, then you have to find an expression for how the probability for these different states look like, okay? And then multiply each of these probabilities with the respective energies to actually give you the average energy, okay? Just try to solve it out. This could be the expression for the partition function. That's very straightforward, right? You have three energy states. Or you can, if you're well versed with how to solve it, you can just directly put in the write the expression for the average energy and solve for it. So basically, see, you have three energy states, E1, E2, and E3. Okay, so Z would be given as e to the power minus beta into 0 plus e to the power minus 2 epsilon into beta plus e to the power minus 4 epsilon into beta, right? So that's your Z, right? Now, how would you define the average energy? That is nothing but, so that's nothing but 0 into probability of being in the 0th state, which is nothing but e to the power minus beta into 0 by Z, right? Plus 2 epsilon into e to the power minus 2 beta epsilon by Z. Again, this term here is your partition function, right? And plus 4 epsilon into e to the power minus 4 beta epsilon by Z, right? So now it's just, you have to just solve it. Okay, so here you can just put in, because you are in the limit where beta epsilon is much, much less than 1, you can explicitly write the, expansion for this exponential terms, okay? And cancel out, and then you would get the value. So that's your answer for average energy per particle of the gas. Okay. This is another question which says that if you have a paramagnetic system which consists of n magnetic dipoles, okay, each dipole carries a magnetic moment mu, which can be treated classically. And the system is at a finite temperature T in an uniform magnetic field H. You have to find the induced magnetization of the system. And then you have to find the heat capacity at constant H. So you can see these ideas of whatever we have been discussing, that's not limited just to, hydrostatic system where we talk about pressure and so on, right? It also, like the same concept comes up when we talk about magnetization or different other order parameters or things like that, right? So here, when you have a paramagnetic system with n magnetic dipoles, it's also a similar kind of problem. You have a magnetic moment. It can have, you know, it can be in different states based on uh, you know the applied magnetic field. So the moment will try to align in the direction of the magnetic field. Okay, and then there are multiple such dipoles, n such dipoles in the system. So based on how this n dipoles are oriented, you would get an induced net magnetization, right? So basically, you have to find something like an average magnetization kind of quantity. And then you have to see the heat capacity, which talks about how this changes as a function of temperature, right? So for this, what you have to do is, you have to find the mean magnetic moment for a dipole. So how do you do it? So it's again, when you're talking about mean, it's nothing but that quantity into the, so whatever the possible values of that quantity into the probability of being at that respective values, right? Summation over all such values would give you the mean. So that's what is being done here. So you can consider that because you have a magnetic moment, like applied uniform field H, and then you have this magnetic moment which you try to align in the direction. So you can consider the moment as, so if you have, what do I say, the energy state or the possible orientations can be taken as x cos theta, then e to the power x cos theta d omega, where omega is now the steradian or the angular change that is possible for your moment to have. So basically, each moment will have a region in which it can orient, right? It can change its orientation. So that is given as d omega. And then you have to do an integration over d omega, which ranges for the entire value of the steradian that it can cover. So e to the power x cos theta d omega. So the summation over all such values will give you again the partition function. And here you want to find the mean moment. So you have to multiply by mu cos theta along with this probability density, right? So e to the power x cos theta d omega by z. Z is this term. So this value will give you the mean magnetic moment for a dipole. Okay. And then if you have n such dipoles, that will include all of them. So now you write the explicit expression for this, solid angle, which is given as sine theta d theta. Okay. And do an integration from 0 to pi. That's the possible range of your orientation of the dipole. And then this is the expression. So this is for a single dipole. Now, if you have many such dipoles, you can multiply it by n, and this would be your expression for the net induced magnetization of the system, which is given as m. Now, when you want to find the heat capacity, which is given as del u del T, so basically you can now write it as minus h into del m del T. So once you know the magnetization, you can find the heat capacity by using this relation. So the same idea of, finding expectation values, making use of the probability density also comes up in questions like this. Okay. Now, this is a question where it says that you have gas molecules of mass m confined in a cylinder of radius r and length L. Okay. And it's kept vertically in the Earth's gravitational field. Okay. This by itself is telling you that you have a potential, right? You have the gravitational potential in action. And now the average energy of the gas at low temperature will be what? So for this, what you have to do, you have to first write the expression for your Hamiltonian, right? For gas molecules under the effect of gravity, we know that you would obviously have the kinetic energies like px square by 2m, py square by 2m, pz square by 2m. You can have all those terms. But then you have a potential in the z direction, right? mg into z. That's your potential energy, gravitational potential energy. So now this is your Hamiltonian. Based on that, now you have to find the partition function, and then from there you have to find the average energy, like U, okay, and go to the limit of low temperatures where mgl is much greater than kBT. Okay, that's the question, right? Can you try to solve it? So see, basically, for, you know, if you just take one particle and then you're considering in 3 dimension, so you'll have 1 by h cube e to the power minus beta h dpx dpy dpz dx dy dz. Okay. Now you will have all these kinetic terms coming in for like dpx dpy dpz, and in the z coordinate you would have mgz by kbt, right? Which is because of your gravitational potential energy. So this is your partition function for one particle, right? So you can now solve for this based on your well-known integrals, okay? And this would be given by this relation that you have here. So I'm not explicitly solving the integral. So once you have the expression for the partition function, now you want to find, this is for one particle. If you have n such particles and if they're non-interacting, we know that Zn will be given as Z1 to the power n, right? So this to the power n will be your net partition function, okay? Now, how do you define energy? So here, what you can do is once you have Z, you can find F. From there, you can find the other coordinates, all the other thermodynamic variables, and then find energy. You can do that. But we, at the very start of the class, we did see that there is a direct relation between the partition function and the average energy, right? And that is given as kBT squared del T ln Z. So now once you have an expression for your partition function, you can directly use this relation to find the average energy. Okay. And here, when you are actually simplifying these terms, you can make use of this limit that mgl is much greater than kBT. Okay, so that will give you the average energy at low temperatures. Okay, so in many questions, there can be situations where you can directly actually use the expression of the partition function to directly find an expression for the average energy, other than finding free energy and from there finding all the different, other thermodynamic variables like pressure and entropy, and from there then using the relation to find U. You can directly find U by using this relation. Okay. Okay. Now here, this is a question where it says that you have a system of n classical non-interacting particles, each of mass m and temperature T, and it's confined in an external potential, which is again, as you can see, has this, harmonic potential form. And it says that it's in 3 dimension. So now you have to find the internal energy of the system. So by now, there can be, like, out of all the discussions that we have had, you might be in a position to directly, answer this question, or you can also solve for it. Okay. So what, if you would like to answer, you can let me know what the answer should be. So It's also straightforward, from the fact that, when we are at a large end limit and in a, when the temperatures are not too low or something. So in those cases, typically when we start with the ensemble theory, we for large n, we would actually go back to the same expressions that we typically get for thermodynamic descriptions, right? So now when you have n classical non-interacting particles in a harmonic potential, and it's a three-dimensional harmonic potential. So from our very idea of equipartition of energy, we can actually comment on what the answer should be. We might not solve for it explicitly, okay? We don't need to solve for it, but we can also solve and reconfirm what the internal energy should be. This is something which we have already done at the very start of the class in the very you know first few questions. We have actually solved this question, but in a different form where we had explicitly used the potential for a harmonic potential. But this is the same form, right? Half a r squared. So now r squared is nothing but x squared plus y squared plus z squared, right? So it's the same form as half k x squared, half k y squared, half k z squared. So it's basically the same thing. So what do you think the answer should be? So if you can write V as half a x squared plus y squared plus z squared, it's a harmonic oscillator. So the partition function is given as this. So this is something which we have already derived at the start of the class, right? So now what you can do is you can directly use this expression of the partition function to find the internal energy using the relation kT squared del T of L and Z, okay? And that will give you 3n kT. Now this can also be derived directly from our knowledge of equipartition of energy, where you say that you have three dimensions, and in each dimension you would have kinetic energy and potential energy, and each of them will be half kBt. So that already tells you that for one particle, the typical, the average energy should be 3 kBt. And now if you have n such non-interacting particles, the internal energy is given as 3n kBt. So that is also valid when you look at it from the, uh, from the point of view of equipartition of energy. Okay. There can also be questions like this, where again, when you're talking about discrete energy levels, or whenever you're talking about energy distributions, you need to be careful about how the energy levels are distributed, whether there is any degeneracy or not. Okay, so you have to consider that when you take into, define your partition function or average energy and so on. So here it says that you have three energy levels, 0 and plus minus epsilon, and the zero state is doubly degenerate. Okay, while the others are non-degenerate. Now you have to find the average energy at uh, in terms of the inverse temperature beta, right? So how do you do it? So for this case, what you have to do basically is that you have to, when you write the partition function, you have to take into account that the zeroth state is doubly degenerate. That means there are two states with the same energy. Okay. So can you try to find an expression for, so once you know the expression for Z or the partition function, rest is trivial, right? You can directly use the relations to find the average energy. See, it's quite simple, right? So when you define energy levels, so now when you write Z, which is a partition function, you have to multiply with the degeneracy factor. So for the zero state, it is doubly degenerate. So you have two such possibilities. For all the other states, the degeneracy is one. So then you have e to the power beta e plus e to the power minus beta e. Okay. So this is your expression for your partition function. Now, based on that, you have to find the average energy. Okay. So that means again, you can do minus del beta of ln z, because here it's written in terms of, like, you can write it in terms of beta. So you can directly use this relation. If you had to do it in terms of temperature, then you can, again rewrite this in terms of temperature. So then you would get the last descriptor, you would use this relation, right, in terms of temperature. And here, because you're using in terms of beta, you can directly use minus del beta of ln z and do this integral, do the differentiation. So that would give you an expression for the average energy. Okay. And this is how it turns out to be. So here, this point is important, that if your energy levels have a degeneracy, you have to consider that when you write an expression for the partition function or the average energy. Okay. Now, there can also be questions like this, where you have n non-interacting spins kept in an external magnetic field B at some temperature T. And then you have the Hamiltonian of the system, which is defined as minus mu B summation over SI, where SI is the, talks about the spin of your individual, uh, non-interacting spins. SI can be plus minus 1. And then it says that what should be the minimum value of mu B by kBt for which your mean spin is greater than equal to half. Okay. So it's also a similar kind of question, actually. So what you have to do basically is, you have to find, if you want to find mean, it's nothing but that quantity. So what are the two possible values? +1 and -1. So you have to find the probability of being in +1 state. You have to find the probability of being in -1 state. And then when you find the mean, it's nothing but +1 into probability of being in +1 plus -1 into probability of being in -1, right? That's the average. So the probability of being in +1 state can be just written as e to the power minus mu B by kt by z. So this is your expression of your z, right? Because you have two possible states, plus and -1. And then probability of being in -1 is again given as e to the power minus of minus mu B by kbt, okay, by z. So this is how it looks like. So now the mean is given as 1 into probability of being in 1 plus or -1 into probability of being in -1. And you can, rewrite this using the expressions of the tan hyperbolic functions. And this would give you the expression for the mean spin. Now it says that what should be the minimum value of mu B by kt so that the mean value is greater than equal to 1/3. This is for one particle. So for n particle, you can write it as minus n into tan hyperbolic mu B by kbt. And then it says that now this is given is greater than equal to 1/3. So you can use this relation to find a value for mu B by kt. Okay. So that's how this kind of questions are to be solved. Okay. So yeah. Now, there can also be questions where you now have a guess of non-relativistic classical particles in one dimension. It's subjected to a potential. You have to find the partition function. So here you have non-relativistic classical particles. So you have to use that fact that, you have a typical expression of your Hamiltonian for that, and you have an additional potential given as alpha into x. Okay. So accordingly, your expression of the Hamiltonian will change, and that will determine the partition function, right? So basically, you can write it as, 1 by h, it's one dimension. So you have 1 by h minus infinity to infinity e to the power minus p squared by 2m kt dpx. This is your kinetic part. And then you have a potential part, which is given as minus infinity to infinity e to the power minus alpha x by kt. Okay. So now the first part, and like you can decouple the position and the momentum integrals, okay, and solve it separately. So this will be your for the momentum part, and this is for your position. So for position, you again have to use, you know, the fact that, so you have a modulus of x, right? So you can break it as minus infinity to 0, and then again 0 to infinity. Okay. So this will give you the part for the, like, this is the value for this part of your integral. Okay. And this is something which you already know from the case for a free particle. So now you can just write an expression for z. Okay. And this is how it looks like. So this is for one particle, and then for n particles, you can accordingly have. So here it's, if you consider one particle, this is your expression for the partition function for a non-relativistic classical particle in this potential. Okay, so this is how it looks like. So your answer should be C. Okay. Now, this is another question which says that, now you can also look at it from the point of view of, in many cases when you write Hamiltonian, Hamiltonian in quantum mechanics, as you know, it can be written in terms of a operator or a matrix, right? And that gives you energy. So when you use the Hamiltonian operator, you get energy of the states. So now from that point of view, suppose if you know that the Hamiltonian is given as this matrix here, and you're asked that, find the partition function for this two-level system. So how do you find it? Okay. So for this kind of question, what you can say is that you can try to diagonalize this matrix and find the eigenvalues for this operator, because the eigenvalues are the energy states, right? The eigenvalues of the Hamiltonian is nothing but the energy states. So once you know the values, eigenvalues, you know the energy state, then it becomes a typical question of a two-level system, similar to what we have been discussing so far, right? So once you know the energy state, then you can directly find the partition function. So that's what you can also do here. So basically, you can, find the eigenvalues, by diagonalizing the matrix, and this is how the eigenvalues will turn out to be. So now these are the two energy states. So that will already tell you that the the partition function is given as trace of e to the power minus beta h. So this is how it should look like, right? So you can rewrite it in terms of cos hyperbolic, and this is how the value is. So in this kind of questions where you have matrix, you can just make use of the fact that the eigenvalues of the Hamiltonian is nothing but the energy states. Okay. So this is yeah, one of the keys. I think that's it. So yeah, thank you. If you have any doubts regarding what we have been discussing so far, feel free to, ask me either now or also later. Okay, so if there are no doubts, let's call it a day. Thank you.